One quick video to cover Chapter 12. This is just mostly terms and definitions, and we'll do the big case study of a ATM, section 12.5, starting on page 556. We'll do that one in class. So we'll just go through sort of the highlights of this chapter, again, mostly definitions. So you might see something called the software life cycle. So this is all activities. Alright, so all activities from initial analysis until obsolescence. So anything to deal with a piece of software. So you know, beginning all the way to the end of that program when it's no longer used. Okay, Department of Defense started this idea of a formal process for software development, sort of standardizing it. And there's sort of 5 basic pieces to that. We got analysis of the problem. We got design of a software solution. Got implementation. We got testing of that program, and then finally deployment of the product. And these can happen in different ways. Okay, so the analysis phase, you decide what the project is supposed to do. The output of the analysis phase is what's called a requirements document. The design phase, you develop your plan for how you're going to implement it. Implementation phase, you write and compile the program code. And the testing, you run tests. And the deployment, your users of the program install it and use it. So this was back in the 1970s, and the software engineers had a very simple visual model. If you look at figure 1 on page 531, and it was what's called a waterfall. Okay, and that was very linear, so it went from analysis through deployment. You finished the analysis phase, and it was very sequential. Analysis finished, then you went to design, then you went to implementation. Then you found out that doesn't really work, right? You get one, you get it out, test it, even if you run it, give it to the users, and they go, oh, this isn't quite right, come back and you got to fix it. All right, so that sort of changed, and they got into the late 1980s. This guy named Barry Boehm, or Bayham, not sure, did this what he called a spiral model. So multiple phases. Each phase ends with the construction of a prototype. Prototype is a small system that shows some aspects of the final system. Because the prototype model is only part of a system, they do not need to withstand customer abuse. They can be implemented quickly. It's common to build a user interface prototype that shows the user interface in action, etc., etc. All right, and that's again figure 2, page 532. So that's a spiral model. So you can think of this as linear, and this is development of prototypes in multiple iterations. You go around before you finally deploy. This is down one phase at a time. All right, then 1999, you get this book called Extreme Programming, development methodology that strives for simplicity by cutting out most of the formal trappings of a traditional development methodology and focusing on a set of practices that, like, everybody's going to sort of agree to. So best practices, and there are several of them. Realistic planning. Customers are to make business decisions. Programmers are to make technical decisions. Update the plan when it conflicts with reality. Small releases. Release a useful system quickly, then release updates on a very short cycle. This is something that Apple is actually pretty good about doing. Metaphor. All programmers should have a simple shared story that explains the system under development. Everybody needs to know what's going on, right? And they all need to have sort of a shared vision and a shared idea how this is going to go. This is kind of like movie animators. Each person's going to draw a different scene or a different character, or even just a part of a character, and it's up to the director to make sure that they all look the same, have the same sort of feel, and then you can't tell that, all right, person A drew scene 1 and person B drew scene 2 because they look different and they act different. So everything's got to be the same. Simplicity, design everything to be as simple as possible instead of preparing for future complexity. Testing, both programmers and customers are to write test cases. The system is continuously tested. Right? I as a programmer might think of some things that could break the system and handle them. You as the user would not think of. However, you as the user will probably think of some things that I as the programmer didn't think would ever possibly come out of this. Refactoring, programmers are to restructure the system continuously to improve the code and eliminate duplication. All right, object-oriented programming, particularly in this way, like we write one thing, once it works, you just use it, you don't rewrite it. Pair programming, put programmers together in pairs, require each pair to write code on a single computer. That is fairly extreme, but the idea being, if two people are working on the same thing and have to work on the same document, this is sort of like a shared document in Google Docs or whatever, that we both can mess with, things will move along and it'll be forced to work all our differences instead of I write part, you write part, and we go to put them together and they don't work. Well, if we're writing the same actual piece of code, then they have to work or the thing doesn't work, it won't even compile. Collective ownership. All programmers have permission to change all code as becomes necessary. Continuous integration. Whenever a task is complete, build the entire system and test it. 40-hour work week. Don't cover up unrealistic schedules with bursts of heroic effort. A lot of you like to do that. You could change that from a 40-hour work week to a 2-hour Andrew Hamilton study session. On-site customer. An actual customer of the system is to be accessible to team members at all times. And coding standards. Programmers are to follow standards that emphasize self-documenting code. And as it says on page 534, many of these are common sense. Others, such as pair programming, are surprising. Beck claims that the value of extreme programming approach lies in the synergy of these practices. The sum is bigger than the whole, or sum is bigger than the parts. But just some ideas. So going back a little bit more into the terms and definitions of programming. So using object-oriented design, you got to discover classes, determine the responsibilities of each class, and describe the relationships between these classes. All right, nouns. So classes are nouns. They're things, right? Represent things or ideas. Generally a noun word. Okay. So if we're doing like an invoice on page 536, you could come up with a bunch of things. Maybe the invoice, line item, or the customer. So when finding classes, keep the following points in mind. A class represents a set of objects with the same behavior. Entities with multiple occurrences in your program description, such as customers or products, are good candidates for objects. Find out what they have in common and design classes to capture these commonalities. Some entities should be represented as objects, others as primitive types. For example, should an address be an object of an address class, or should it be a string? Depends on what you want to do with it. Not all classes are going to be discovered initially. You're going to write them and go, oh, I actually need to add this part in to handle this a little bit. That's fine. And some of the classes you need may already exist either in the standard library or in a program you already wrote. All right. Methods. Those are generally verbs, right? Things that are happening, commands, action, all right? Things that need to get done. And then you have to figure out which method goes with which class. Okay. Moving on to 12.3, page 539. This one this is a good one you do need to know, in particular this part, is a, has a. Went over it a little bit already. Inheritance, the is a relationship is sometimes inappropriately used. Aggregation, so this is inheritance. This is what's called aggregation. Okay. This is subclasses, and this means aggregation means that one class one class has references. Okay. So if I had, for instance, a tire class, should a tire class be a subclass of circle? Maybe. There are quite a few useful methods of the circle class. All right, but it isn't true that every tire is a circle, so it wouldn't be a nice, well-done subclass inheritance. Tires are car parts, whereas circles are geometric objects. A tire has a circle as its boundary. Okay. If you're going to use an instance field, then it's probably aggregation. Okay. So if you looked at public class tire, you'd have private string rating maybe, and private circle the boundary, the edge of this tire. Technical term for that would be that's aggregation. Each tire aggregates or has a circle object as part of it. Okay. Every car, another example, every car is a vehicle. Every car has a tire. Okay. Thus, you would use inheritance from vehicle and aggregation of tires. So, for instance, if general rule of thumb, if it's an instance field, It's some sort of aggregation. It has a relationship. Figure 6, page 540. I've got vehicle, car, tire. And then if you look on page 541, you'll see the inheritance symbol as drawn, and you need to know to be able to identify the pictures. Solid line with a solid line and an triangle arrow tip is inheritance. Interface is a dotted line with a triangle tip. Aggregation is a solid line with a diamond tip. And dependency is a dotted line with an open tip. Okay? Aggregation is a stronger form of dependency. A class depends on another one if it uses an object. Okay? A class can use an object, but it might not actually make an object of that type. Okay? So example, a class may use the scanner class, but never define an instance field. It may have a local variable or may be a parameter. Okay? That's not aggregation. That's dependency. Generally, you need aggregation when an object needs to remember another object between method calls. It needs to save it, so you're having an instance field. That is aggregation. And if you notice the little yellow block on page 540, you need to be able to distinguish the UML notations for inheritance, interface, aggregation, and dependency. So that figure, table 1 on page 541, is a good thing to know. Okay, 12.4, doing this invoice. Useful bit would be the diagram on page 548, figure 7. I got an invoice, have an address, got a line item, and product. Okay. Notice diamond head here. So aggregation line items are going to have instance fields and create objects of the product class. Invoices are going to depend. Oops, that's a bad one. Invoices have a dependency on the product class. So it should be a dotted line, an arrowhead. So we're going to use products, but not actually save or create objects of them. We might have local variables or parameters, and then address also is a aggregation as well as line item. All right. And then you can go through the actual implementation. Formatting on page 553 is kind of interesting. It shows you how, if you want to do things a little fancier, how to do that. Got an address, going to add some products. Notice on page 552 in invoiceprinter.java, we add anonymous products, right? There's no objects, right? So dependency, not aggregation, right here, because we don't actually save them. They don't have names. We're not making objects. They're anonymous ones. We are making objects, but like they don't have a specific name or anything like that to get back to them. They're going into an invoice array. Product, address, line item, pretty straightforward stuff. All right, so that's chapter 12. Again, mostly terms and definitions, and we'll do 12.5, the